All right, I think it's started. Welcome back, everyone. Today we continue on working in this game engine. So we started on trying to get rendering working, but there were a bit of prerequisites like hierarchical entities and how do we do transformation before we could actually render loaded 3D models onto the scene. So we'll continue that by, you know, finishing up the loading system, but also how do we architect this entire thing. So this process node that we were using, if you run it, it will directly show you that there's this weird incorrect cube that shows up on the screen right now. Because this was a load model prototype that we had initially created. It's a incomplete function, right? And there's a new complete one, which is just load model. So that's the one we will take a look at. All right. So what do? We haven't created it. So let's create a definition. How would this work? So each model will be an entity in the game object system that we have. So all of the components within all of the parts of this model will show up as children to this entity. However, each entity also requires a few other things that we need to take into account. So, sorry, not entity, but like each renderable object requires a few more things that we need to take into account. So, what are these? First, we will have a list of triangles that we have to draw that directly come from a buffer. Then there's a list of primitives, which is a list of triangles. All primitives have their own material index. So each primitive will correspond to one material, and each mesh can have multiple primitives. Each mesh has one transformation that is attached using a node. So each node has one transformation and up to one mesh. So zero or one mesh. And finally, all of this data needs to go somewhere that we have to have allocated, let's say. So let's start. First thing that we would need is to begin all of the loading that we have done using CGLTF. So for that, I'll just copy the header that we had used. Well, not header, but just the initialization. So there, all of our code has been initialized. Return false instead becomes a null pointer return. And here we will have few more things. We will end up with a CGLTF free GLTF model. So that frees the data. The model is gone. And we can then return at the end the entity that we create. We don't have it yet. So we will say entity pointer entity. And that entity is the one we push out. All right. So again, we already have entity manager. So we are good to just say entity manager, create entity with the transform, vertices, and texture file. What is the transform for this thing? We can construct it. So designate initialization, position is 0, 0.0, 0, 0.0, 0, 0.0. Okay. Scale is 1.0 and rotation is XM quaternion identity. So we close that and we move on. It needs a set of vertices, we give it nothing. It needs a texture file, we give it nothing. So this we hadn't finished last time. We wanted to create another function for creating entities that wouldn't necessarily require everything. It wouldn't require meshes, it wouldn't require texture files. So let's get to it. I will remove those. So we just create an entity. Each entity does have a transform, so that is guaranteed. We create a definition for this. And we go and look at the old create entity that we have. Let's see, where is it? Entity manager.cpp. This is the one. All right. So this one first creates a mesh, then it creates a material, and finally, after all of this is done, it creates an entity. This part is key. So what I will do is I'll just copy that and I'll paste it here. All right. So now we can just return this entity and life is fine. Okay. So here instead of the alloc, we will be returning entity which you have to create. So entity pointer entity equals entity manager create entity. So it's just create entity with the given transform entity mesh equals, right, mesh has to be moved, which means this cannot be done. We will have to set mesh somehow. So little thing I will do is I'll remove these from entity, because right now I'm saying that each entity has mesh and material. Let's remove that. That's an assumption we won't make anymore. So each entity only has a transform that's necessary for it. 1 second. All right. Each entity only has a transform that's necessary for it. And we will say that it can have a mesh or a material. So here we'll remove this. Okay. So entity can have a mesh or material. How do we check that? So we make different types. So we have a basic entity like this with transforms and everything. And then inside models, we can use specific types of entities. Mm, okay, this is going to be interesting. Entity doesn't have anything. It can have a mesh. So we can say mesh pointer m mesh. It can have a material. I know we've done this m material, but it used to be objects. Now we're making it pointers. So now we're making it pointers, and we can just say create a getter and setter for these. So generate code, getters and setters. We only want it for mesh and material. Getter and setter, etc. Access right is public. Return by reference. All of this is fine. That creates those for us. All of that also just moves into a different location. So we will add them right after the transform getter. So mesh, instead of returning a reference, will return a pointer. We'll return a pointer here. Set material is similar, and set mesh is similar. Fine. Build. Will fail a lot of things. entity.mesh, and this becomes hyphen buffer. Mesh is missing const qualifier, so let's add that because that has to be const now. Const, and that has to be const now. Fine. Build. Texture, so here again becomes arrow operator. Okay. Create entity doesn't care about those. Here entity has set mesh, takes a mesh pointer. Where do we get a mesh pointer from? We have to create a mesh somewhere. So again, entity manager, and we will add mesh creator, mesh creation stuff in here. So along, other than the entities, other than just the entities, we will add a mesh array. So meshes, and we'll add a material array. Material. There is a change. There is a small difference that we will have to make. What do we need? So we will need to have free lists, which we don't have currently. So we'll have to add free lists into the system. But for now, I will just allocate them and without, like, not allow deallocation. It's just for now, right? Here we take entity, we take meshes. I'm doing fine, thanks. It's working. I just need to do the architectural stuff, and I'm being very stubborn. I should probably just use something like Flex, which does entity component systems, or I should go complete object oriented. I shouldn't do this middle ground. Meshes better, and material becomes materials. Hey, loops in your language. That's nice. I wonder what the syntax. What is the syntax you're using? Hey, so that constructs materials for us. All of those also need their own counts and capacities. Ah, what a pain. What a pain indeed. So, anyway, materials and meshes can be allocated there. Material, we'll need the count of meshes, so UN32T, mesh count, material UN32T, material count, entity count, next. So that renames things for us. And then don't actually we don't actually use that ordering because it'll waste a lot of space. So now this is fine, right? Things would just work. So what we'll do is we'll take the capacity and we will construct everything to the same capacity. So we'll take a pessimistic view saying that number of meshes would be equal to number of maximum number of meshes, maximum number of entities, maximum number of materials is all the same. Loop 10 output a plus 1. Not bad actually. Loop 10 is easy. You could even say repeat 10 instead of loop. It's easier for people outside to understand. I'm just talking in terms of like usability things. We work on this syntax stuff as a part of research, and understandability for novices is quite an important aspect for new programming languages. That's kind of why Python is so popular, right? Because it's very easy to understand for new people. Okay, where was I? Look at me, forgetting where I was. A maze. I mean, for computer scientists, like if you know how to program, sure, right? It's all the same. But for people outside, a loop, not necessarily, like just saying loop doesn't always make them understand that you mean this, while repeat is fairly obvious that like you're going to repeat the next things. I'm just undoing everything I did here because I have a feeling I'm going to not go with this method that I was trying. So what I'll do instead is I'll take this padding here and I'll just add flags in this because I'm anyway wasting that space, right? So I'll just call it flags. Had left it in a to do, but while I was cleaning my code, I forgot to correct that. Okay. So entity creates flags. That is fine. It may or may not add the other things. How do I allow meshes to be may or may not exist, right? Because meshes need to be constructed due to the existence of this buffer ID here. So actually, they don't necessarily need to exist. What I can do is bool has value or is valid. Actually, has value is better. Has is valid. Sorry, is valid because that's something we've been using for a while. Return buffer dot. We can check if buffer is null, or we can just yeah. So we'll check if buffer is null. Null, null. So null is actually a static that returns something. I will add another thing here which says is null to make things a bit easier on checking. So no discard bool, and all it does is midx return index equal 0, right? So it is null is true if index is 0. That allows me to just check is null, and it just does buffer dot is null, and that's also a const function. No discard. All right. Same for materials again. Copy paste. This also has a padding really. Uint 32t padding 0. Same wasted space. We will come around and fix those later because this will not remain the same by the end of this. So texture dot is null or sampler dot is null. Okay. Now with that, these mesh and materials cannot be used as they are. So I'll change this to a pointer return. Pointer return again. And I'll say that if so, I think for more cleaner code, you could use object-oriented programming. Yeah, but it's also slower code if you do that. This is temporary. I don't need hierarchies right now. I don't need to bother with all of that because then I'll have a class which is like with this thing with meshes, then one without meshes. But then at the end, I'll have to read through those and find if they have a mesh or not. Might as well put them in an array and just check if they have a mesh or not. So this is a different kind of uh, programming pattern, let's say. But what I'm doing right now is just exploration, right? I'm not actually I'm not actually using this. Like this is not going to be my final code. This is just something I'm doing quick and dirty with the idea that it will actually be quick. Yeah. There's no difference between struct and classes except structs by default are public, which means anything you write inside a struct is public unless you say private. And in class, everything is private unless you say public. That's it. The only thing that changes is default. So here, if I change the name, because I already say private and public by like manually, changing between class and struct doesn't do anything. The only difference is it adds a bit of work when I try to forward declare things. Either I say class entity here or struct entity here, but that will have to be correct. So now instead of having to check if render device is a class or a struct, I just call everything a struct, and it makes life easier because then everything is just forward declare struct everywhere, right? Anyway, coming back to why not OOP, other thing is it makes the allocation a bit difficult as well. I will have to write a more complicated allocator that can handle different elements of different sizes. Meanwhile, here I just say everything is, of a size, and either it works or it doesn't work. So yeah, we have a mesh and we have this thing. Inside a mesh, we can check. So if m mesh is null, so if it is null, then we return a null pointer. Otherwise, we return an actual pointer. And I'm aware I could actually do an optional here for cleaner code, but since I'm the one writing it, I can do the check, right? If anything returns a pointer, you're supposed to do a pointer check. Okay, so what else is happening? Take some mesh. This thing is, I can generate that one as well. All of these. The std forward just passes it forward no matter what it is. Really, it's not required. So here I can say move, which is probably more accurate anyway. But even if I say forward, it would be fine. So in this case, I don't do anything. I just say material and mesh get their default constructions. So m mesh does a default, m material does a default, and that's it. We will generate the declaration. That's it. So now these will automatically be null. That's the default constructor that we have. All our IDs are by default null. So build plenty of these things. Create entity because it's only taking a transform without anything else because we did not add the second one. We have it. If I remember correctly, we do have it. Yeah, it's right there. We just don't have a declaration for it, right? So we add the declaration back. Entity count plus plus should be fine normally. Oh, did we do count plus plus? Yes, we did. We undid the whole thing. So set mesh. Instead, I can say create entity, comma. No, we cannot say at all. Entity. I do know Minecraft, yes. What about it? Redstone, yes, you can make a computer with it. So that's alloc for entity, and it can take the other things as mesh and material. Move, move. So that I can say this is an entity, and that's entity, and then return the entity. It's a bit of a stretch to say it can run Minecraft because Minecraft is relatively very complicated and redstone computers are very slow. You can make a 16-bit computer or an 8085 emulator, but otherwise, not much. Not much helpful. Destroy entity does material and then destroys it. We need to check if entity material. So we'll take it out. Material pointer material equals that. So if material, then we destroy those things from the material. Seriously? Like, I really don't think that can be true. But we need to check this out now. At some point, I'll look it up. How can they? I mean, with very bad performance, a limited subset, I suppose, can be done. Then this becomes material buffer. Sorry, it's a mesh buffer. All right. So now this will ensure that it's delete like entities are being destroyed properly. Entity count undeclared because that's just count now. Build. We succeeded. Let's run it once, and we're back to where we started from. Promise is not a rickroll. To be fair, I love Rick. Like I love uh, the song. Never Gonna Give You Up is definitely one of my favorites. So even if you rickroll, I'll laugh about it. Like I really enjoy getting rickrolled. Okay, fetch buffer unchecked cannot be const. Anyway, where were we? So we were trying to load the models. So let's go back there. Model loader.h, model loader.cpp. We created the entity with nothing in it. So that needs to be handled. Create entity with nothing in it, right? And yeah, of course, I'm not about to watch YouTube on while being live on YouTube. So entity has been constructed. What next? So entities are going to be nested. So nodes inside the system will effectively be these entities that are being loaded through. So if we go and check load model prototype, we come here, we get the scene, so default scene, and we go through it to process all the nodes. All right. So each of these nodes should be added as a child for the entity. So entity add child, and it will take process node as an input. What I'll do is I'll go to the process node, sorry, and I'll rename it to process node prototype because we will have to redo this to a certain extent. And that's process node prototype here. And then here instead I'll use process node. So this one actually does process nodes, right? So all the entities would be created within the process nodes, and all it needs right now is the nodes, so the node itself. And this here gets copied to make it duplicated. That one is a prototype. And this one is the actual, where we don't have the positions and nodes anymore. So why don't we have positions and nodes anymore as separate things? Simply because we would not need them. We're not going to add things at the process level anymore. So entity pointer, process node will add its own entities. This needs to generate a definition. I will move that all the way to the bottom. And now the node gets processed. So what's in a node? So process node, as the prototype goes, it's node prototype. So this is process node prototype. It takes a translation, so it processes the transformation here, and then it processes the mesh if a mesh exists. The way we are going to do this is to copy all of that first. Then these things are what we need to get out of the particular thing, particular data. So get node transform, or really we don't need to right now. This is fine. This is just fine. This will get the data that we need. That's the transformation. So here we should be able to create a new entity. Entity equals entity manager dot create entity. We don't have entity manager here. So process node needs to take an entity manager pointer entity manager, and down there we just pass forward the entity manager. Here we get the entity manager in. Okay. Manages manager, much better. So inside process now we can create the entity by doing entity manager create entity. It needs a transform. We have all the data required for a transform, so we say transform, and we can add the position. That's v translation. No, actually just translation, scale, and rotation. So rotation we call it Q rotation. So we'll add it that way. Okay. Now mesh, if it exists. If it doesn't exist, then we don't have to add a mesh. So process mesh will simply load a mesh there. Again, I'll go up to the top to the process mesh. I'll call it process mesh prototype. All right. And we will that seems to be missing here. There we go. Okay. So meshes are a unit. Each mesh has multiple primitives, but these primitives don't have their own transformations, which means they don't need to be a part of an entity. A mesh is the terminal entity. That means any node or any entity that has a mesh is a terminal entity. It can still have children, but it's like we don't have to further add additional nodes that don't exist. So process mesh, we don't have prototype anymore. Decimal number system will be hard for us to create computers really. The reason we use binary is because on and off is very easy for transistors to manage. We don't have anything like that for 10 values, right? We can put currents, we can say voltages, and every 1 volt is a value. But voltages can go off, like they can be off by a 0.1 or something, or if your voltage fluctuates, everything goes wrong. Meanwhile, in our computers, either it works or it just doesn't work. It doesn't give us, I mean, it does give us invalid values nowadays because we're going so small that quantum effects can cause issues, but otherwise, no. The Soviet Union did try experimenting with ternary computers. So it's off, on, and negative direction, right? But eventually, once you had binary things just working, people went along with it, right? Why why do more than what is simple and required? So what does a mesh do? So mesh will return us a, well, mesh process mesh, and it takes in it cgltf mesh stand, not const expression, just const mesh. So it's not this one. This will guaranteedly give us a mesh, but a mesh must exist. So it's on the user, like on the creator, to ensure. Process mesh here will take the mesh if the mesh exists. So we will say if node dot mesh, then we do that. Here node dot mesh gets dereferenced to make it go inwards, not inwards, but like go in. Entity set or entity mesh. Uh, that normally does not work. I will create a setter actually. So void set mesh takes a mesh as a and says m mesh equals. This should only happen once. So if m mesh dot is null, so if it's sorry assert, so we assert that m mesh is null, and then we just add that in. So now we can just say m mesh equals std move mesh. Okay, so this should be init. What's wrong with this? Never moved. Fine. Let's just write it that way. And that doesn't work, huh? Okay. I'll call it init mesh instead, just to make sure that it's clear that it's being initialized here. Init mesh, and we take the mesh. Okay, we don't have that in place anymore. Now when we go to process node, again we don't need prototypes. Here is just node. It will take a child dereferenced, needs an entity manager first, so we pass down the entity manager, takes the child, returns an entity which will be added as a child to the previous entity. So entity add child, and we do that. Okay, so this will continue. It will nesting, like in a nesting way, it will automatically set all of these up for us. Next question is, if the material is null, how do we render things? So that directly gets the data from the system, but we also need primitives actually. We haven't yet processed primitives. So process mesh is process node. It doesn't return anything, so it has to return this entity. Okay. Process mesh, which we haven't completed yet. Let's process mesh here. Generate the definition. Copy that over. Go to the bottom. Paste the mesh over here. And now each mesh has primitives, has a set of primitives. So all of these primitives need to be collected in here. How do we do that? So we say mesh dot primitives count. So I have to do the array thing. I have the code from our prototype, so we go there. This is how we collect a mesh. So we copy that over. Okay, we don't have this. Not mesh is not possible. Mesh dot primitives has to exist. It's a guarantee. Once this is done, for each primitive we get the position data. It gives us the start and this thing, and it takes positions here because it will write into the positions vector that we had. We don't have it right now, so we'll have to manually write this. So inside load model, we will create two buffers, dpmr vector. This will be vertex or positions, which is different, but let's take vertex now. We're using the original meshes. Verts, vertices. Then here after entity manager, we will pass in the vertices. So process node needs to be refactored there. So that became process node. That wasn't what I exactly wanted, but okay. That's the process node we're actually looking at. Mostly it's fine. This is just node and we're done. Hi, vertices. Okay. Now we go down. Vertices is there. Inside process node, it needs vertices here. So std, pmr, vector, vertex, pointer, vertices. Now it has vertices available to it, which it will pass down here and to meshes. So inside process mesh, I will pass down vertices. Process mesh needs vertices, std, pmr, vertex, so vector or vertex, vertices. It's a pointer, so pointer comes in, and this needs a declaration. So we just copy that and we'll paste it up there where process mesh is currently sitting. Okay, what next? So positions are taken from here. Sorry, positions are given in here, so that's vertices now. Extract position data will actually create vertices and it will write to the positions in there. So this becomes vertex. Vertex start, vertex count, that is fine with us. Positions becomes vertices. Okay. So vertex start is the vertex size. Vertex count is the total number of count for vertices that we found. We copy that into the from the accessor to the data. That doesn't work anymore. So this you have to be careful with, right? The vertices data here is no longer just pointers to positions. So instead, the unpacked data will have to copy itself into another buffer that we'll have to randomly create. So std, pmr, vector, xm, float 3, vector float 3, positions equals vertices. So positions, and it will take the allocator of vertices. So vertices dot allocator. All right. Now here I can just say that. So position attribute dot data, position attribute dot data. Okay, that is fine. Vertices data. This one is the one that has to change. The resize here should not only do it for those vertices but also for positions. So positions also require a resize. It's local, so it's a dot. Positions dot data. That doesn't need a vertex size vertex start anymore. It just needs a count. So that will copy all of it, and then for auto, and we'll replace the auto later, but auto and position in positions, then we take a auto vertex iter equals vertices dot begin. Now we're guaranteed from before, so guaranteed to have space for these vertices, and then we can do vertex iter position equals position from the inner data. So we just copy this like this and add a const there if you want. Can add a const here if you want. We can replace auto with explicit types. Replace auto with explicit types, so that is kind of painful, so it's better not to. And that's that. It copies. All of that is automatic. Like all of that is done. We will have positions, vertices constructed from here. Okay, so that is vertex data. What next? So extract position data. It tries to out mesh. The mesh here is a model mesh, which you don't have. Instead, it will be primitive. So Go to model mesh. We look at what we have. So we have these extending counts. Instead, I'll call them primitives. So struct primitive, which has a uint32t start, uint32t count, and this becomes a vector of primitives, right? Each primitive also has a material. So we'll have to do material here. Okay. With that done, we can now just like push this material stuff into our little model here. So this model is the allocator for it, has nodes, which we don't need anymore because the entity will handle that. Vertices, we don't need anymore because again, our thing will handle that. We will need primitives, so std pmr vector of primitives. Okay, this will be indexed by the meshes. So for each mesh, it will index into the primitive. We will also need materials. So std pmr vector material. So instead of materials being at a level of entities, they will be at the level of uh, models. So this model thing. So it has that material and primitive here. That much is done. What else do we need from this? Not much that I can think of. We have entity manager, we have render device in load model, so it will be able to create all of those for us as we need. What we will also do is we'll get all the material. So current scene doesn't have materials. GLTF model, materials. So you can see it's an array again. So for uint 32t material index, so it's 0, material index less than current scene, material, no sorry, GLTF model, materials count, plus plus material index gets us a material and we need to process this. So we need to process all the materials. So again, std pmr vector material materials. So here inside from this material we will process it. So it's a process material and we'll pass the materials as an array in here. Makes it easier for us to manage all of them. Create a global function called material process, like process materials. That is fine. This will be a constant reference. Copy that, paste it at the top. So now model mesh is no longer a thing. Actually, that we don't care about it anymore. So we delete that. Can delete extract position data we still use. Delete model prototype. Delete this. Process mesh prototype is being used by process node prototype. Again, that too is gone. GLTF model materials. Material index. What's wrong with that? Comma, semicolon. Okay, process material, generate definition, copy, paste it at the bottom here. What does the material do? So material contains all of this detail, which is a lot of detail. None of it we are currently using. So the only thing we will check is if it has albedo. It's called diffuse then? No. Albedo, diffuse color, normal occlusion, emissive, color transmission. No, none of those. PBR, but that's not the one either. Interesting. The texture view has normal texture, occlusion texture, and emissive texture. There are no other texture views here inside GLTF material. Um, what GLTF reference? The material contains buffer view. This is materials. PBR metallic roughness, which has a base color. Base color. That is actually the PBR metallic roughness. This thing here, and we'll have to check if it has the PBR metallic roughness or not. So back we go. Has PBR metallic roughness? If, and then we process that material. So process PBR metallic roughness material dot PBR metallic roughness, and similarly create if material dot has PBR loss specular lossiness, then we put that in, right? Okay. With that, that's how we process materials. But right now, this model doesn't have any materials. So we'll make that assumption and we'll say process materials actually doesn't add anything to the model, right? So it does go through it. The process is still called, it just doesn't do anything. So inside process mesh, what we end up doing is we take these position data which we get, which gives us a start and count. We then say primitives. So we don't have primitives here. We'll need to get that. And if you notice, this is starting to get a little, that goes away. This will start to get a little complicated because we'll start adding a lot of these functions, not functions, but these vectors here. So we can just pass the model into the remaining things. So once we are done with load model gets here, we try processing meshes inside this, which means that is the one that needs the model to exist. That is the model here. And process node can just take model instead of taking anything else. I mean, it will have other things too, actually, but it can take model now. So we say model pointer model, and at the top, we have to go at the top and say again the same thing. Inside mesh, we take model. No, this was here. Takes model pointer model. Okay. So what's happening now? This allocates its models, process material. Process material will. This formatting has been completely messed up, which is sad. Transform, transform equals transform. Oh, was it just because I forgot a comma? Yeah, it was indeed just because I forgot a comma. It's now aligning with these vertices here, so output data's better. Okay, so that is an output data. So inside process node, it will get a model. Based on this model, this needs to pass it forward. So model gets passed forward. And mesh here, when it processes it, it will take vertices and model as well. So model first, then vertices. Takes a model pointer model first and then vertices. Model pointer model first, then vertices. And so when we get to this point, instead of manually doing anything with the primitives, we say model primitives pushback star, or really we can do emplace back here if you want. So start comma count. Okay, that gives a start and count in our position copy. Currently, the start and count that they give you inside a primitive itself will be the wrong one for us. Okay, so in the primitives which we've gotten here, so we will copy that out as a cgltf primitive stand primitive. So then we can say primitive dot attribute, primitive dot attribute count. Here I can say primitive dot material, attributes, attributes count, material. Oh, it actually just points us to the material. So in that event, we would not load the materials separately. We'll instead pass the material in and we'll just get an index out of it. So here we can get an uint 32t, right? And instead of getting the material through that, we can check. So if primitive dot material, so if material exists, then so here uint 32t material index equals 0xff, so uint 32 max. So if material is existent, then we will process the material. So we'll say material index equals process material. We'll give it the materials pointer. Where do we get that from? It's inside model. So model dot materials, and we give that no process node, process material. It already exists here, right? But this becomes model pointer model, as we do everywhere. This becomes uint32t. The materials don't need to go in through this process. This is no longer used anymore. So process material takes model directly and it takes the particular material. So primitive dot material dereferenced, right? So this gives us a material index which we can directly pass into the emplace back. Cool. So that creates primitives for us. Each primitive is automatically created in the model, and all we care about for this given mesh is a list of primitives that it will access. That's all it ends up to, right? The mesh just becomes a set of primitives that this mesh will access. So again, many ways of doing this. I'm going to cheap out slightly. Instead of even taking the mesh here, which was, so this is an external mesh, this is a different mesh. because it needs a buffer and everything. This inner mesh should just be an entity. Okay. And instead of allocating anything else, I will just push these primitives into the entity. Here, when I said an entity has a mesh, I said an entity has a material. I will add a few more things. So I'll say an entity has a model, model, and an entity has a primitive, which is a primitive. We include the model loader here. It's not an issue right now. Okay, so effectively, we've just kind of cheated the system. We've added the model and primitive into the entity, which means entity has everything, which is not necessarily how it will end up. But for now, this is fine. And no, that doesn't check out either. So when you say this mesh, it normally means a model now. When you say material, it will be part of model. So all of those will be separated. But when you process a mesh, at the end you have an entity which will have a mesh. And this mesh will contain a list of primitives. So the model mesh that I had initially claimed would be accurate, would be good to use. So model loader, model mesh, which is just a vector of primitives. Model mesh would be fine to use. So now I would say each model will get those model meshes pasted into it through primitives, through entities. So each entity can have a model mesh. Okay. And it can have a model. Or actually, I'll skip having a model, possibility of having a model. But it can have a model mesh, right? And I will return a boolean here is null, as we have for everything else. It returns if primitives dot empty. Okay, so we consider that if there are no primitives, then the mesh doesn't exist at all. Okay, so with that we have the model mesh. When we do a load model, we can attach model meshes to a given entity. As you can see inside entity manager, the entity is getting a little painful to use. So temporarily I will remove this private from the newly added stuff. So I'll here say public private, and we can continue. So inside load model, after all of this is constructed, we have a model, we have all of this, that is fine. Process mesh could not convert model to mesh. Yeah. So instead of init mesh, this will be dot model mesh equals, and we copy the model mesh in there. Okay. So that's model meshes. Process mesh here. It's already declared with the return type of model mesh. Should be entity. Okay, that node is the entity and it has one mesh. So model mesh it is. Right. And at the end here, so when I create the primitives, I place them back into this system, the models primitives. Ah, that's what I did. Ugh, my bad. So this model mesh just needs a single index. Two indexes. Uint32 primitive start and uint32t primitive count, and is null actually should just return primitive count equals 0. So if primitive count is 0, model mesh is not used. Okay, so with that, this becomes relatively cheap to use. We do the emplace back, but before we do the emplace back, we will count all the size of things. So primitives, we have the primitive count already. We just need to know where it starts. So u in 32t primitive start equals model dot primitives dot size. We might as well cast it while we're at it. That gives us the starting point, and when we return, we can just return the primitive start followed by the count, which comes from mesh.primitive count. Again, we'll put that up here. U in 32t primitive count, right? That is U in 32. No, it's GLTF size. What value is GLTF size? Is size t. So static cast, right? So primitive start, primitive counts exist. They're both constants. Oops. Const, const, and primitive starts, primitive count. So it'll just return that. We still need to grab other attributes. I'll write that there, but do nothing with it. Some error somewhere with a semicolon missing or something like that. Transform unknown override specifier. Node does not support C++ int. Transform comes from entity manager. Entity manager depends on model loader. So that obviously doesn't fly very well with the system. So what I'll do is I'll remove the transform from here. We don't have the nodes. We don't need them anymore. We will even remove the vertices soon. But for now, I leave them here like this. Material becomes a question. Entity manager, entity, all of that becomes a question. All of these can be forward declarations. So we don't have to include anything. Okay. So with that, we have forward declared all of those. And so all we need is in model loader CPP, we need to have these created. So there we will have to include entity manager.h. Fine. This much is okay for us. Primitives have been created. Model has been more or less generated. Let's see what we end up with, right? So when we end load model, so in model loader, when we finish load model from here to here, what do we end up with? It didn't build at all. Okay, let's see. Prototype not found. Yeah, because we don't use that one anymore. It needs an entity manager, render device, and a file name. File name is same. It needs entity manager. So and that's a app state, render device. Do you think I have render device? Out. App state. We just have app state. So app state dot render device dot it's entity manager. App state dot entity manager. App state dot render device. Load model needs entity manager and render device. These are in fact pointers, so that is fine. Okay, so that will give us a load model. What it does is it returns an entity. So we can't really, I mean, we can assert it, but it will be incorrect. So entity pointer, entity equals load model. We can assert the entity here. We shouldn't need to do this anymore, right? None of that needs to be done anymore. This can be const. Now we can run it. Ideally, this should just work. It did not. Okay. Render device is an unreferenced formal parameter. We don't use it because we never created the vertex buffer. That's okay. These are all warnings. So why did it fail? Process material must return a value. Return 0. No, return u in 32 max. That is the invalid value that we're using. Sentinel. Okay. Unsigned external symbol called process material has been called. Potential matches are here. So let's see what the process materials function is. Have this process material takes a model pointer and material constant reference. That is fine. Like all of that is correct. Is reference in process mesh, this process material, which is right up here, as far as I can see. So what is the issue with this being called? Ah, because this one doesn't take model pointers. Build. Now it should be fine. Yeah, run it. The debugger stopped here, which is fair. More or less exactly what we want. So it says vertices is 0, materials is 0, primitives is 1. It is start 0, count 24, material is like -1, but in the uint32 range, and that is fine because it's adding to this vertices instead of the vertices inside the model, which is also fairly expected because the model shouldn't have vertices. So this is gone. Okay, now what? So once we have our model, which has been created to this point, the model itself needs to have a buffer. So this itself, the so-called mesh that we had at the start, we need to generate that. Actually, there'll be two separate things: mesh and model. I don't see a point in having them separate, so might as well merge them, right? So this will be mesh, which contains an RID for a buffer. So buffer ID there. It says it's a vertex buffer, so vertex buffer. All right. The other thing was counts. We don't need them anymore. Primitives will handle the counts for us. So that should be a model. Here we've had the model. We've done nothing now. Here we need to create the vertex buffer. Another thing that we have is inside Entity Manager CPP, we have a part that does create buffer. Oh, we never switched this, huh? No, that's a staging buffer. Create vertex buffer right there. Just takes a size byte and then we write to it. Like that's all the code there is. So inside model loader, CPP right there, we will create this. So we don't have a vertex count as a variable, we just need this. We don't even need to convert it. We can't get vertices.size bytes. So instead we will take vertices.size times vertices dot vertices 0 into size of. Okay, that gives us size of vertex bytes. This render device buffer manager. Okay, so far so good. We don't need vertex count from here anymore. That is fine. And finally buffer is just buffer. This one becomes model dot vertex buffer. We write to it and we write to the buffer itself saying model dot vertex buffer is to be written with given vertices. Takes a span, right? Oh, is there a PMR span? Don't tell me there's a PMR span. There's no PMR span. STD vector to span. Vector to the spans constructor. PMR vector to span. Doesn't work with the PMR vector. Does it work with a normal vector? It does not. What went wrong? Takes any arbitrary data, right? PMR vector vertex. This one can take, let's say, vertex. Let's help it a little bit with that. That's fine. So if I tell it it's a vertex, that is fine. If I don't tell it it's a vertex, that doesn't work. It's kind of unbelievable. Now it's fine. Ugh. But okay. So that writes to the buffer. Let's see if that we did write that in the entity manager. But anyway, never mind. So this writes to the buffer. That means we have the model vertex buffer being completely constructed. Now we'll go and just pack that into entity. Instead of having model mesh, it doesn't have that at all. Instead of having mesh, it will have a model, possibly M model. Okay, so it may have a model and it may have a model mesh. It does need a model mesh. Okay. Ooh. Here the mesh gets converted into rename all overloads to this one becomes model M mesh M model now. M mesh is M model now. So M model can be null. How do we say if it is null? So bool is null, vertex buffer dot is null. If it has a vertex buffer, a valid vertex buffer, then we're fine. Otherwise, we're not. Okay, that was not what I was wanting. No discard, better. Okay. Ooh, let's go back. Not here, there. The entity is constructed, it's been added here. Inside entity manager.h, we have a model, we have a model mesh. These are the possible things that you can have. Inside model loader, we don't want anything, we don't particularly care for anything. Load model is fine. Extra manager, that's okay. Load model. Okay. We do have to change the destruction of this. So in entity, there's no mesh. So this can't exist. But there is a model, so we can do it with a model. So personally, I think I will just remove these, both model and material, which is, I mean, we have that one already. Model, default, M model mesh, default. Okay, this is fine. Model already has a default constructor. How? Our ID buffer doesn't. It has a default constructor as well. Material doesn't have a default constructor. Why? Reasons I'm entirely unaware of. But okay. You see, we don't need materials. We leave it in actually. We'll do private on this. We'll leave those public. That way I don't have to deal with the constructors at the moment until the design, let's say, is complete. So that simplifies everything. And this doesn't need to have an M before it anymore. Build will have errors. this mesh thing doesn't exist at all. So all of the like the ones behind us would not be correct. So inside create entity, this is removed. So this is the only way to create an entity now. Entity cannot be assigned. It can only be moved. So instead I'll say entity.transform. Entity new, we call it in place on this entity. Entity, and you can take transform. There we go. Okay, that initializes the entity for us. If not is in it, create member function. I think we deleted it. If it doesn't have any of the above, it's not in it. But we don't care about that anymore. We actually do is in it on a per object basis. So here we don't do just material. We will say if material, then we delete it. So again, that doesn't exist. It just say dot is null. So if material dot is null, this is a not. Then material dot sampler is deleted. Entity material dot texture is deleted. If not, entity material, next is model dot is null, then model dot buffer, vertex buffer. So we do that. For model, there are two more. So what else do we have? Transform. We have transform, model, material, and more, and the last one. There, in that particular case, we don't actually need much. We can just say model mesh, and we can say it equals 0, 0, -1. UN 32. Primitive start, primitive count, material index. Why is material index not okay? Oh, right. Not a part of model. This one is just 0, 0. Good for us. And similarly, each of those inner things, entity.model.primitives.clear, entity.model.materials.clear, right? Or alternately, entity model dot clear. Now let's do the individual clears followed by entity the allocator, which we won't do anything with right now. Okay, that has failed. Let's see what's wrong. We construct in Blaze the entities for the walls. We don't have those walls anymore, like the rotating planes, rectangles. So we have to remove those. Entity.transform, simpler. Transform, model, material, material, This is a little bit of a cheating at the moment. These materials are going to be bound on a per, what do you call it, per primitive basis. So vertex buffer, which will fetch and bind, will only happen if there exists a vertex buffer, right? So here we do fetch buffer for the vertex buffer and we do it. This is okay. That one will automatically ensure that the vertex buffer is only bound if valid. Here we want to bind texture. We don't have textures right now, so I will just skip the texture part. Okay. And command draw will only exist if there is a primitive to it. So if entity dot model mesh dot is null. So if it is not null, only then do we draw this. And what do we draw here? So we don't go for that. We go for model mesh dot primitive start. So the vertex, sorry, primitive count. No, primitive count is primitives. We have to iterate through the primitives now. So we paste world transform for every node. If it's a model mesh, there is no longer any nodes. So here we've done a model, we've done this. This has to be manipulated outside of the structure. So what I will do is I'll just say model pointer prev, no, not prev, but current. I'll say there's a current model that we definitely need to have. The model pointer for the function. The current pointer is something we need to have if you want to do anything. Here, when we use the model, so we'll say if entity dot model dot is null. So if it is not null, then current it's not there. So when we do the children. So if it is entity dot model dot is null, if it is null, then pass current, whatever is above us. Otherwise, entity dot model is what you pass. You know, pass model const as a this thing. That's fine because this can be a const. Okay. Now that will recursively go into the drawing thing. We'll go try to draw entity. Draw entity is here. This needs a current which will be null pointer. We have the world transform. If model mesh is not null, then we take primitives for it. So sorry, not here. For uint 32 ti prim idx equals entity dot model mesh dot primitive start prim idx less than entity dot model mesh dot primitive count. Nope. Plus plus prim idx. So for each primitive, and now for each primitive, actually life can be made simpler. Primitive ampersand primitive. So for each primitive, inside current primitives, this is a span. So we'll say std span from primitives dot begin plus vertex start. So that's entity dot model mesh dot vertex start, primitive start, with the size of entity dot model mesh dot primitive count. This can be called data. That will be fine. That gives you a primitive. constant. This is fine. So now we get primitives. So for each primitive dot count. So that goes here. First goes here. So primitive dot material, not material, sorry, dot start. That's first vertex. Everything else is fine. We don't particularly want to look at anything else. But textures will eventually be bound inside this. So the material will be bound here on a per primitive. So build solution failed again. Model mesh is not a part of entity. Yeah, M model mesh is not a part of entity. Build that ran, run it. Okay, that's fine. Run it. Some error. Big, some big error. So app iterate. We tried to do this. It went inside. Tried to do that. Went went further inside. We tried to take the data of primitives. Current dot primitives where current is null. So if not is null, and I'll say primitives. So current assert current. Current must exist if we have any model meshes. So that is fine. Let's actually do a breakpoint and check what's happening through this process. So we get current is null. Fine. Has the transformation is done. There's no vertex buffer, so we skip that. Command push constants. Put the world transform in. Entity.model mesh is null. It is null, so we don't do anything. Since it is null, we don't pass entity.model. So when we go into draw, yeah, that is null. Current is still null. So vertex buffer will have to be bound if there is any. So it returned true, is null is true. So we go back in, current is still null, vertex buffer is still not there. But model mesh has one primitive, right? Model mesh has one primitive, but current is still null, which means at some point this vertex buffer did not get assigned properly. So we can go to entity manager, no, model loader, and put our breakpoint there and try again. So when you come to entity that we're trying to return, that is all right. Like we go to first child. This is the second one. Model mesh is nothing. Model has current. Model has a 0 on the vertex buffer. Did we assign the vertex buffer? We did. So model.vertex buffer is a valid vertex buffer. Fine. Did we assign the model? We did not assign the model. So here we will, instead of passing anything else, we'll just say entity.model, right? Because at the end of the day, we're just pasting things into the final model. We know there should be a model here. And now if I start, it should give us a cube. Please give us a cube. Did not give us a cube because we hit a breakpoint. Still didn't give us a cube. No real errors though. So what happened with that? Let's check the shader code. What are we doing in the case there are no colors? So we go for interpolated colors. What are the interpolated colors? It's 0, 0, 0 because that's the default value. And when we created the vertices, we never set the color here for the interpolated colors. So just to check if we have a model or not, instead of doing anything else, I will just try debugging it in RenderDoc. And one second, I think there's a problem with the stream. Um, was it working? All right. I don't know why it said the bitrate was having an issue, but anyway, oops. So, mesh viewer, we don't have any meshes here. Draw 24, we do have a mesh, and it does seem to be drawing a cube, or not. All of those seem to just be in the z direction. Something collapsed somewhere in there. Actually, the data doesn't exist. This is only one of them. Okay, so the vertices created are wrong. Ah, turned off Visual Studio by mistake. So go to the model loader, BP. We do the extract position data. Take XM float, vertex iter. Ah. We forget to continue iterating on vertex iter. And no wonder iterator being constant is wrong. Okay, we still don't see anything. Not completely unexpected. No, don't save this capture. Okay, don't care about that. This is the mesh. So we do have a mesh, right? We do have a mesh here. It does seem to be a single mesh. There is only one draw call. So that looks correct. Great. So now the next thing is to check the spec. So there is something known as base color in the material. So even if we don't have a material, there is a default material. So GLTF, default material. So the default material must be used. So what is the default material? All default values of material apply. What are the default values? So PBR metallic roughness is not required. If parameter set is used to define material, then when undefined, all default value of metallic roughness must apply. What are the default values? Base color is 1111. Base color texture is not valid. Metallic factor is 1. Roughness factor is 1. All of these need to be added into our material. So for that, we go back to our entity there. In here, we will go through the materials. So we have a sampler, we have a texture. That means more or less nothing now. We have wasted space, which is no longer wasted now because we'll put base color factor here. So XM float 3. I think it takes a float 4, doesn't it? Yeah, the spec says float 4. Okay. Uh, XM float 4. How do you do half precision floats again? It's fine. We'll do the compression and stuff later. So this one is base color, and that is still wasting space really because this is 32 bits. There's a gap between these. So we'll put a float there, which is meta roughness. There's another float which is metallic. So it's not like we don't end up wasting space at the end. What else do we need in the material? Extras, no, no, no. This is required default. Metallic factor, roughness factor both have required defaults. Base color texture is not required. Color factor has a required default of 1111. So color factor, we got it. Metallic, roughness, let's actually align them like this. Sampler, which is a completely separate thing from everything else right now. I said reuse, but we have to make a sampler manager for this. So this is to copy directly. I say to copy directly. This will just, get sent. Base color is 111. We can change the alpha of the base color, so we have to leave it in per the spec. And we can add another. Well, we can leave the uint32t padding 0. Fix me wasting space. We'll leave it in. Okay. So materials have more details now, and we can start unpacking the materials. Instead of just unpacking default, this is a default material, which means we need to be able to have something created, constructed, that is default. Do we need something like that? Not necessarily. We just say this is 1.0. Roughness is equal to 1.0f. Metallic equals 1.0f. Okay. Texture and everything else will handle itself. On the side of bindless, on the side of the slang code, the PCB per instance data, it has a transform and the RID. We'll now have the other material details. So float 4 for base color. Then we'll have a float for metallic, float for roughness, and there should be an alignment here. So u in padding, right? That's all we need. Quote correction, that's all we should need. We have to check if that's all we need. We go back to miscellaneous data because inside here we have a range, push constant range, where we say it's XM matrix plus the size of a uint32. But now we have more things. So we have a size of XMM vector 4 and all the other things. So instead, what I will do is I'll just say plus material, which is 8 plus 16 plus 8, which is 16 plus 16, which is 32. Right? I'll just constant add this. And this I'll put it as size of material. Oops. Size of material. Fine. So that is working itself out. I'm going to check the audio. Check the audio. Okay, that seems right. So continuing on, we've got the material. We should be able to build this and run it again. Okay, that was fine. And the reference material, that's also completely fine. Now in the Blaze code where we're trying to render things, we will push constant. Okay, you. Ah. Okay. But instead of just taking material or texture, we will say it's 32. Size of material PCB data. And here we'll say material dot texture. So why are we doing material dot texture there? Because we want to give it only the data from texture onwards. If you run this, nothing happens. There's an error here. There's a push constant buffer lock buffer block with a range 0 to 104. Okay, that doesn't make sense. Like that shouldn't occur. So let's look at what's happening with Underdog. We launch. No, run it. Don't care about that. We check the pipeline state, vertex shader, fragment shader actually, because we want to check PCB. All right, so PCB has data. So base color is 1, metallic is zeros, when it shouldn't be that. But we can also see this. So transform is 64, goes until 64. Texture is 4 bits. Oh, sorry, 4 bytes. Adding then should take another 4 bytes, right? So going from there to padding should take just another 4 bytes. Instead, what it's ending up taking is space equivalent to 2 more floats. That's because the system expects you to have alignments that are aligned to vector force. So here inside texture, I'll do this in a simpler way, which is I'll copy it like this. And that is enough. Like that will fix the problem. Or that did not, in fact, fix the problem. Okay. Let's see what's wrong. Oh yeah, that's wrong with that. We also need to write it here. So these are 3 4 bits, 4 byte, 4 4 byte systems. So that aligns everything to 16 bytes. And that happens if only the shader has compiled. We need to rebuild everything. Okay, start. All right, that is correct-ish. The reason I'm saying ish is because we have this whole thing with vertex color being sent, which is being multiplied with the base. But currently we don't want the vertex color to bother us like this. So I will just say 1.0.xxxxx, right? And you run it. Yeah, right. We just change the shader. Rebuild everything. Start. There we go. We have a cube and it's rotating along a very weird set of axes because we take every entity and we rotate every single entity in the system. Right? Now, the next thing to do would be to go forward. So, load normals. All right. So, mesh loader here just loads data for one part of the vertex. So, the vertex is not entirely loaded. Secondly, vertex is currently in this, which it shouldn't be. That like makes no sense. So, we move that to this place. Now, instead of having a color, we want a normal. Okay. We already have the rest more or less written as it should be. There will probably be one change in this data which will say there is no normal. Yeah, see, normal. These are our sets of arrays, vertices for the whole construction. We don't do that anymore, so we can remove all of that. And you can see the code has simplified so much. Now inside load model, we have to write to the normal data. Hold on, run build again. There should be a problem in mesh. In miscellaneous. Yeah, there it was. Because miscellaneous tries to do a size of not there. Attribute description. It does a size of color. We don't have color, so it can't do a size of for that. Build solution. Okay, now it completed. If you run it, it won't work because the normals are not in the right place. So what we need to do is we need to go to model loader and set up inside load model. We need to set up the no, it's process mesh. We need to set up extract other datas as well. So position, copy, paste, normal. So now that's normal data. So instead of position data, we can say extract normal data, right? Extract normal data is undefined. Create global function extract normal data. Yes, but we can go here. And if you notice, this part is roughly all the same. Only this part changes. So what we will do is we will copy all of that as a separate thing, right? So that goes out. That goes, no, let's actually use tools for this. So refactor, extract method, call the method extract accessor data. So now it takes vertices. We don't want it to take vertices. Takes position attributes. That is fine. We want that. It takes positions. We want it to take that. Vertex start and vertex count, which it takes by constant reference as inputs. We don't want to do that actually. So next, and that extracts the data for us. Okay, what's missing? So extract extracted data, or rename it. Extract accessor data, sorry. So this will copy all the position attributes into positions, into this. And then for each position, we can start writing there. What we don't have is vertex start and vertex count anymore. So what we'll do is vertex start, we'll cut it and we'll paste it right there. This was wrong anyway, so this we can fix like this. Yeah, not sure if it's even worth it to really have this as a separate function at all. So undo position, that's normal. Now extract position data, that's the position data. I copy all of this and I paste it right here instead, right? So now position attribute instead just becomes something we need to get out. So CGLTF accessor, or is it attribute? It is attribute. Constant position attribute equals attributes attrib index, and that should handle itself. Start becomes vertex start, count becomes vertex count. There is a bug here, so I'll fix it. We don't need to allocate as many as vertex start. It's only for vertices.resize that we need vertex start plus vertex count. And this we can again put here instead. That even makes sense with the comment, right? And in this particular case, even vertex start can be moved right here. And we can manage the cast right now. Okay, so that is one. accessor. Then we copy this whole thing with the accessor creation, but instead of adding primitives, we will only check for the other accessors because position is a guaranteed accessor. The rest, not so much. So normal and everything are not guaranteed. So here, what we end up with is we remove that and we just write this here. Now, here's a funny set of things that happen. First, position attributes need to be renamed to normal attribute. Second, positions needs to be renamed to normals. Vertex count similarly becomes, actually that is still correct. Normals are resize, we write into this, and then followed by that, we take the vertex start. So here is the problem. We don't actually take vertex start. Okay. Vertex start for a given primitive is here. So vertex start needs to be moved all the way up there. Okay. Because vertex start is per primitive. And then this will automatically handle itself based on the first one to resize it. The others will just see resize and they'll know up because you already have that. Similarly, vertex count that we set up in here, this can be moved outside the scope. So this becomes vertex count and we put that here. It won't be const anymore and is equal to 0. The vertex count will automatically set itself every time. It will try resize. So this one it will resize, which is fine. This one it will guarantee to resize as many as we have accessors for, which should be the same for each of them anyway. So vertex count here will just be an assignment. We do a resize again, that just works. This becomes normal. And here we'll say dot normal. Okay. So that's vertex iteration again. Go from vertices dot begin, which is wrong. So this is vertices dot begin plus vertex start. We need to prime it with vertex start. That's how much forward we are moved before we even start this process. So nice to find the bug ahead of time. So this load model will now add the normals. In an ideal situation, this should just, I guess this is becoming like a thing where I just say it should just work and it does not. Extract position data, we don't use it anymore, so off it goes. Conversion, conversion. So float count is size t by 3. Static cast. Again, static cast. Material and stuff are formal, unreferenced formal parameters. We don't care about that right now. Run it. Still have it. Okay, so far so good. Mesh slang. So inside here we have color input, which now is actually normal. Vertex color here, let's set it to normal, which will be unique, but let's look at it anyway. Float 4 got vertex float 3. So float 4 comma 1.0 build. Let's build, like rebuild anyway, because we just modified a shader. Start there. So the issue is some of these normals are actually negative. So we will normalize it by saying, so this is minus 1 to 1. So we'll say plus 1.0. So now this will be 0 to 2. And then we'll say divide by 2. So multiplied by 0.5. And now you will have, yes, of course, rebuild solution. Okay, start. There we go, right? This one seems to have some issue. This one end that has some issues for reasons unknown. We can check that using this thing here. So launch, no, that captures it. We need it to the right spot, so let's wait for it to come out again. There we go. Captured a frame. Okay, now what? So if we go into command draw, inside this, we can see fragment shader reading some push constants, reducing some values, picture, transform, okay, rasterizer, we don't particularly need to know about that. In, out, this is fine. Position, screen position, vertex color. So vertex color is what we need to look at. 0.5s and zeros. These are all very flat coloring schemes. To all. So right now I don't have a clue why it's being flaky, right? So what I'll do is I'll just set the colors to positions for a second and then we can check it out. So that is position dot x y z. So that will just take positions which go from, if I'm not wrong, they also go from -1 to 1. So maybe I need to handle them too. Okay. So right now that side is not giving us any trouble, right? That issue only happened when we used the normals. We say normal.rgb, run it again. Okay, you had some issues. Build, rebuild. The blue part still has that given issue. This one is 1.0 f plus, we can write it with a zero point 0.5 f plus zero point 0.5 f times. I mean, it still has, that's getting annoying. Still has that. Okay. What else can be the issue with the normal? I can't, sorry, I can't say. Looks similar to what is known as Z fighter, but it's not really Z fighter. We can go to the thing again, so render doc, launch it. There's a hazard there. It's interesting. Okay, with the capture, you can look at the frame itself and see what's happening. Look, this thing. So you can see it's like a Moire pattern, Moire pattern. I don't know how to pronounce it. But here you can see this goes from zero point 0.5 when it tries to move. So this vertex here is z is equal to 1. Okay, the whole thing is z equals 1. But here you can see the z actually changes. Z, whatever I'm going to call it. So at the end here, z is 1. Up there, z is 1. Up here, z is 1. There's no reason why the z shouldn't be 1 here. It is interpolating somehow, but I don't see why that error is occurring. Okay, but let's normalize this. So build normalize not a member. Normalize build. Okay, need to rebuild it because SDL restart. Okay, we've done normalization on the colors, and that still gives an issue here. Now that doesn't make any sense. And the reason that doesn't make any sense is because if you normalize a vector, it will go into colors based on, no, I mean, the colors will be fine. It's just that once you normalize it, it should not give those weird color schemes. Okay, hold on. Interpolated colors, normalize. Let's try this. We normalize interpolated. I there build rebuild. Okay, start. All right. Still has the issue even after normalizing this. That's interesting. Times. So what happens if I give 1.0 dot xxxx, right? Start. Rebuild solution. Start. But to me, the white doesn't seem to be having any issues. Perhaps if I switch it to gray, I'll see something. Uh, Need to fix it. Nothing. We have the base color now, so we can do. Uh, it's called PCB dot base color, which is supposed to be the color to be sent back. Really. Or still seems to be giving us a whole bunch of nothingness. Oh no, 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 that's not it. Yeah, so we have normal now. Call it a normal as it should be. This is normal. Okay, normal dot normalize RGB. But when normal takes like a float 4, but that space is anyway going to be wasted if we don't use it. Float 4 normalize, comma 1.0 here. 0 0.0 actually. Okay, what else? What next? So once we have the normal, we can do a primitive lighting calculation. So going to be very basic, very incorrect. The way it works is first I'll change the name from interpolated colors to interpolated normals. So of course normal. Singular. Okay, there's no interpolated colors anymore. We can remove that. It just gives a texture sample. But now we can do the lighting calculation. So we can say interpolated normal, interpolated normal there. So it has to be normalized before and it also has to be normalized after. So normalize. I did forget that before, didn't I? So you have to normalize it after because normals do not linear interpolate correctly. I mean, linear interpolation doesn't lead to normalized normals. So we normalize it. We say let n equals this. Okay. Now with n, we can say lighting calculation by saying, let's say lighting is at 111. So we can do dot product. So dot between float 3, hold on, interpolate normal dot xyz dot normalize, that becomes n. We say float 3, we take 1 point, or we can just say 1.0 dot xxx comma n, that gives you the dot product. This is let light factor, okay, and then we multiply this by light factor. Cool. Let's try. Build, run, rebuild, run. That's interesting, right? Something's completely corrupted with that particular part. Keeps doing it. Hold on though. So light factor should be a dot product between 111 and normal. 111 is actually away from us. Okay, so float 3, we can say its x-axis is positive 1, so right hand side. Y-axis is positive 1, so top, and z-axis is negative 1, so in our direction. That looks incorrect. Supposed to be a dot product between these. Light factor is a float that is supposedly correct. Yeah, it is correct. Oh, okay. Here's what's happening. The normal also needs to move according to the PCB transform. Currently, it's in the world coordinates. Sorry, it's in the model coordinates. It needs to be in the world coordinates because that's what we're trying to get everything into. And here again, having 0, 0, 0 helps because that means the normal does not translate. How many times am I going to make that same mistake before I remember every time, eh? There we go. That is similar, like more similar to what is expected. But you can see the normals being entirely wrong on that side because they can light up even if they're facing away. Something somewhere is exceptionally problematic right now. Look at in dock, mode last setting, launch, that's not it. Nope, I didn't catch the right frame at all. Close, no to all, close, no to all, launch, no. Okay, that should be fine. There. So texture viewer again. Those normals are pretty static. These normals seem to be all over the place. Hmm. Let's try painting normals again. So N, rebuild. Alright, N is a float 3, so float 4 takes an N comma 1.0 F. Build, rebuild solution. Start. Okay, there's a little bit of that blue color that showed up. As for why it's showing up, I'm not sure. Is perhaps one of the normals actually wrong? So we can check. These are the positions. That is the normal. So first phase normal is positive Z. Second phase, are there four normals? Okay, that checks out. Second phase, no, no, that is entirely incorrect. It did four of these. So it did one, two, three. Ah, I know exactly the issue now. So this is something we talked about before. We were using a type of thing called triangle strip. However, what GLTF is currently using is triangle list. And so not using so using triangle strip makes it wrong. That is much worse. That was much worse. Okay, so what's up with this, right? So when we load the model, let's check what's happening in there. So inside load model in model loader.cpp, when we are returning from load model, let's check the state of the vertices. Start. How many vertices do we have? We have 24 vertices. How many should we have? So a cube has 6 sides. Each side has 2 triangles, so that is 12. Each triangle needs 3, so that's 36. Am I doing something wrong? Let's do it again. Each cube has six sides. Each side has two triangles. So that's 12 triangles. And each triangle needs three vertices. So it doesn't have that. 24. 24 is 8 times 3. That's 8 triangles. That's all it has. It has 8 triangles. But why? Let's look at the GLTF itself. So box GLTF, and you see the nodes has children there. It does have a material actually that we do need to take care of. But it's not embedded, so we'll go one step up. One more step up, embedded. Here the buffer is written inside as an octet string. That doesn't help us. So, right, it is 24 there. It is 24. Its name is mesh. Pull out our GLTF converter. No indices. It has a mode 4, so primitive mode. Let's check. Primitive, so GLTF. Actually, you can check it in the specification. This I'll shut it down there. But in the specification, you can check mode. Yeah, so mode. Default is 4. Otherwise, you can have a specific mode. This one has a mode 4. Okay. What are modes? So let's check all the possible modes. Mesh primitive modes. 4 is triangles. That is triangle list. We have 24 vertices. 1, 2, 3 makes 1. 24 vertices, 0 indices. Material is 0. Oh, no, its indices is actually 0. It has an index buffer. Has an index buffer right there. So the box is not vertex only. Okay, so the box uses something known as index buffers. What are index buffers? They're a way to index into the vertices, into the vertex buffers. So instead of drawing the triangles like point 1 to point 2 to point 3, then drawing a second triangle and you having to rewrite two of the vertices, you use the index buffer to actually index into these triangles. That is more efficient overall, but we currently don't support it. So in order to add index buffer support, we'll have to write index buffer support. So let's do that while we're at it. So first we have entity manager, which has a mesh, which has a buffer and vertex count. We don't use this anymore. We have model loader, which has model here. Where did it go? Here, which is a buffer ID. We need a second one. This one will be index buffer. So load model, and we have vertex and index buffers. Good for us. Now in model loader.cpp, here where we create vertices, we'll also have to add another one, which is indexes, un32t for indices, right? And I'm going to pack this into, no, I'm not going to pack this in. I will pass this down, but I will pack, yeah, I should pack this in. So I pack this into an outputs structure. So that's what process node. Nah, never mind. Indices. CD, PMR, vector, indices. Index is UN32T. pointer indices. There we go. So nothing here. Process mesh will use indices. Process nodes will use indices. And we can copy that and paste it in the top level process node that we have. All the way up here, process node, and we pass indices. Okay, now what? So it took all of those. Process mesh doesn't have this, so create the global function, be that process mesh gets replaced exactly like this. This is mesh indices. Oof, got the wrong names here. Second. Okay, that's it. So it's nothing right. So why should I even bother? Indices. Okay, so that gives us indices in process mesh. So there inside process mesh, we should be able to use these. Process mesh. There it is. Again, we need to paste EMR vector UN32T pointer process mesh. Sorry, indices. So we have indices now. 110. Okay. We have indices now here inside. We do primitives, which takes a vertex start and vertex end. It will also have an index start and index end now. We wouldn't care about index actually. We wouldn't care about vertices anymore actually. So uh, primitives are already there. So per primitive, if you look at it, primitive dot indices, right? There is a way to extract all indices. We should do this first. So for uint 32t in the wow index. I'm just going to call it index. So idx rem index. Oh come on. Index idx. Fine. Index idx equals 0. Index idx less than indices. Index idx plus plus. Okay. Less than or not equal to really. This will be index. So there should be a count somewhere. The targets, mappings, we don't care about those. Okay, that didn't work out. What happened? This is attribute, that's an accessor that has position attribute or data size. Okay, we need to unpack these indices. We don't actually need to iterate through them, we just need to unpack them. So let's get back to it. CGLTF accessor index. You already have the index accessor. That doesn't look like, no, that is another thing. GLTF accessor read index. Nope. Unpack indices. Yeah, that's the one I want. Finally, accessor is nothing but primitive dot indices. Out is the index buffer. How much do we need? I don't know, so we'll do null pointer. Out component size of uint 32t really, but make it indices dot size of indices 0. Index count, this I need to remove like that. Index count is 0. This returns us how many index we need. So size t const index count. So now we know how many indexes we need. Really, this is vertex count. So even though we set it to 0, it's actually that, and we don't need this anymore because those are guaranteed at this point. So positions dot resize vertex count is fine. Vertex count is assigned up there. It's a size t, which is also fine for this. There's a second vertex count somewhere else. There. That goes away. Vertex count is fine. This one is float count, which is nothing but vertex count times 3. Positions dot data. Then no, vertex count times, yeah, it's vertex count times 3. There's also similar thing to do in this one. We don't need vertex count. This can go up there. Float count. Again, we don't need this. Just need that. How many do we need data? We need exactly 3 times the number of vertices. Vertices dot resize. Again, we don't have to do this. No, we do have to do this. So the thing is, index buffer indices and like indexes into this primitive. Okay, and it does consider those offsets automatically, so it will offset itself with vertex start by itself. However, the vertex start and vertex count that we're using are not the same as the index count. So the thing I'm doing here with vertex count setups is wrong. This actually is index count. Okay, so that's not good. We don't have a vertex count anymore. We have an index count. So vertex count will have to be fetched through the unpacked floats thing. Float count is 0. This thing is null pointer. And vertex count is vertex count. So vertex count. However, we don't need this globally anymore. So I don't have to set that up at least. So we set up the vertex count, const, positions are aligned. Goes in, resizes positions based on vertex count. Sizes now, it's actually float count. So float count, vertex count times 3. Sorry, float count by 3. Vertex count times 3 becomes back, like we go back to float count, right? We don't need the vertex count anymore. Vertices dot resize. So this we do have to do. And that we can resize by positions dot size. So the positions are only written for whatever we're using. Okay. That's done. Here it tries to emplace vertex count into the primitives, but we don't do that anymore. This turns out to become much better than before. So we use this. And that's normals. That's normal attribute. That's normal attribute. Normal attribute. This is actually normals, not normal attribute. Here vertex count again becomes normals dot size. So resizing vertices. Shouldn't need to, but we don't know which one comes first, normal or position, so we do it anyway. Will be no up if The size isn't a problem. We do need the vertex start, which is assigned up here, which is correct. It's not the index start though. Vertex iterator, that is fine. Grab the other attribute, that's okay. It grabs the indices. We need to resize now. So indices dot resize with indices dot size plus index count. Okay, index size becomes start. So size t const index start equals indices dot size. This can now be index start. So we resized it, then we can write into it. So we just copy this, paste it here. Index count is now index count. Indices is out component size, that is fine. Out null pointer is indices dot data. We resized it, so that's not correct. Plus vertex start. Okay, and that should work. So that should copy all of the indices into this. So let's actually run this and we'll see what happens, like how indices look at the end of the day. So when model loader finishes loading here, we will stop and we'll see how indices look. So vertex buffer is fine, but indices are here. We haven't set them yet, but you can see they just look, they're just all zero. That's wrong. So let's go in and check. Process node, no. There. Here we try to write the indices. So vertex start, we write there, index start. Okay. Small bugs sometimes. Index start is 0. Do that. Indices now have 36. They're still 0, 0, 0, 0. Okay. Out component size. What is that? So let's check it inside this itself. Out component size. Component type. Component size. Out component size is smaller than index component size. It returns a 0. Okay. We can check. We can do an assert 0. Assert index count greater than 0, which it is actually. Yeah, it's 36. I mean, it resized, so obviously it's 36. Size of that is fine. We go in, let's jump in and check what's happening. Component size is some weird value that doesn't make sense. No, hold on. Might just be because it's not run. Yeah, component size is 40. Indices 0 is 40. Why is it? It's UN32, right? It is UN32. It is UN32. So indices, index 0, because it's a word, it's vector. Indices 0 is a vector. This is not going to work. So instead, it's actually this that I want at 0. And then I need to check if I'm actually indexing vertices. Yeah, so vertex buffer does it, but here vertices is not a pointer. Okay. So you can see these kind of errors occur when you do not know the type, if it's a pointer or this thing, and you kind of make mistakes because you don't pay attention. So we instead say p indices. So now it's easy and it's clear for us that this is a index. So now if we run it, stops here, you can see the indices and you can see 0, 1, 2, then 3, 2, 1. So it goes like through the vertices that we already have. Okay. With that, we have indexes. We need to create an index buffer. So this whole thing gets replicated again. This is index buffer, create index buffer, indices dot zero, indices dot size, index buffer dot value, the model index buffer equals that. Now create index buffer here. Create member function there for create index buffer. We can just take void for now. We don't need anything else. So we already have create vertex buffer. All we have to do is copy it up there and then mirror everything else. Optional buffer ID, index buffer, and everything else is the same. Generate its definition. We can see it's right after the vertex buffer creation. So that's also relatively easy for us to do. We just take the vertex buffer, we copy it right here. Nothing changes except the usage becoming index buffer bit. Everything else remains the same. I will do a rename because I call it vertex buffer here, right? Index buffer allocation. Other than how you use it, these are at the end of the day just buffers. So you don't particularly care if it's like which kind of a buffer it is, so long as you keep a track of it outside. And outside, we know in the mesh, we know that it's a index buffer. Okay, inside Blaze, where we start rendering, when we use vk command draw, we try using primitives directly with a particularly bound vertex buffer and index buffer. So here I do fetch buffers for both for vertex buffer and index buffer. Right? It's value or null pointer. So if you have vertex buffer and index buffer, I'm not checking if model is valid. So maybe I just do that instead. So entity dot model dot is valid. So is null. So if not null, so this is a model, then we will do all of the rest. In which case I can just do value or here. This can be an assert because it needs to have a value. Guaranteedly needs to have a value. In which case this I don't care anymore. And that simplifies things, right? We also vk command bind index buffer. What's in an index buffer? So first you take, I can do it like this, command index buffer, offset is offset, and index type is vk index type uint32. That's it. So we're bound index buffers. Done. Draw indexed. Okay. So inside draw index, we do primitive. So draw index takes a few different things. Okay, see, vk command draw indexed takes a command buffer. That's fine. Index count, which is primitive dot star count. Instance count is 1. First index is primitive dot start. First offset is primitive dot vertex offset. We'll add that. First instance is 0. Okay. Now we have to start with this. Create vertex offset in 32 because you can actually offset it as you like. Start becomes index start. Actually, I don't want to do it there. Index start. Count becomes index count. And so we get index count, index start. But more importantly, inside the Not this data. Model loader.cpp. We can check for primitive start, primitive that we don't care. Index count, index start, those are available to us. Inside primitives, so when we push a primitive, which we are not doing yet, we've completely stopped pushing primitives. So here, after index is done, we push a primitive. So we push a primitive by saying primitives push, not that one, p model primitives push back primitive designate initialization. So index start is available to us. Static cast it. Index count is available to us. Static cast it. Material is available. It's zero. It's a uint 32 max. So default material. Vertex offset is 0. And we'll see if we need a vertex offset. Okay. But right now we'll just default it to 0. To do verify. That's good enough. Start. Okay, it gives an entity here. If we run it, it might just run. No, a bot has been called because one buffer is still allocated. So that's nice, right? Like it tells us what is not deallocated yet. The buffer is index buffer because when we destroy model, we don't destroy index buffers. So inside destroy entity manager cpp, destroy entity. So we do buffer free. We haven't done index buffer free, so index buffer freed, and we're done. Build solution. Start. So that runs, that closes. All good. Mesh.slang. Now let's see here. We passed normals here. Okay. Is anything being rendered? Render doc, help us. Launch. And we don't seem to have anything here. So let's check. It does draw 36. Mesh viewer, it's doing this with the mesh positions, that's the inputs, and you can see they're all wrong. Cancel. And I know it's not that hard to track why it's wrong either, because all we have to do is go to this little thing called model loader.cpp, where we create the index buffer, and there's the issue. We never write to it. Index buffer indices. So what happened is it just kept indexing into the 0th element because everything was defaulted to 0. There we go. Right? So it's now drawing things, it's coloring things in a unique and weird way because the normals are now world normals. So that is also expected. And that's a mesh for us. We do need to load materials. So let's get to that. Model loader. We have the material set up. Everything is set up really. All we need to do is go down there. That's the wrong one. All we have to do is go down here and uncomment this. Okay. I will say assert metallic roughness. So assert has metallic roughness. And we just proceed with that assumption. Right? So you get us a material and we proceed with that assumption, we construct a material. There is a little issue, not entirely an issue, but sort of concern with doing this, which is materials are loaded with index. Multiple things can use the same material. We do not want to reload the material over and over again in the process of like loading materials, right? So what we want to do is we want to cache them at some point. Right now, I'll just say to do cache materials while loading, but later on, that's something we can leave for later, right? Now, for material, PBR metallic roughness, which we kind of guarantee ourselves, base color factor, that's what we need. So material dot material out material. Hmm, actually, let's do it as base color factor. So XM float 4 base color factor equals this. Base color factor is an array of floats. This should XM float 4. This should just work. Yeah, that worked. Okay, wait, it was already working now. It's an explicit constructor. Now, we got base color factor. What else do we need? We have base color texture. So we can take that directx text material dot PBR metallic roughness base color texture. That gives us what is known as a texture view, which has scale, text quads, texture. So we go in there and we get a texture itself. Then we go here. There's a sampler and there's a basis image. We don't care about basis image. We just care about the normal image. Now, what does image have? Again, we go to a buffer view. What's the buffer view? We now have a buffer, right? The image. Let's see if there's a CGLTF load image. CGLTF load. Nope, there is not. CGLTF load image. So, yeah, buffers an image. For buffers, you can use load buffers. That will work out. For data URIs in image, you might need load buffer base 64. All in the headers. So we can look at that in the headers. The image is right there. This GLTF image, which has a buffer view and a URI. Buffer view, which gives you other things. And yeah, that has a buffer, which is a pure data. This is pure data now. Which URI. So we can get a URI out of it. Let's check this URI out, right? So auto underscore equals this. We'll put a breakpoint on it and we'll run it. So now we have this URI. Can't read it at the moment. PBR metallic roughness, base color texture is, yeah, right. There is no base color texture on this one. So we'll do that later. Texture loading we can do later. Let's get to the next step. What else do we have? So our out material will also have metallic and roughness. So metallic, which is float, metallic equals material dot metallic, which is inside PBR metallic roughness, metallic factor, roughness factor, and roughness Okay. Finally, material gets pushed in. So model material dot pushback needs a sampler, needs a texture, needs a padding. Ooh, big amounts of work, right? Null pointer, default, default, roughness, metallic, and base color. That's it. At the end, once because we're pushing here, so index would be IDX. So we went 32 material. One second. Yeah. Material index equals model materials dot size. The casting, and then we return this as a material index. Okay. So this will automatically handle materials for us. Const, 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 const. That automatically handles materials for us. So we should be able to use it. Hold on. We are not using it in the shader. So let's go back, build, rebuild all, start. So that's with the directed light that's coming from top left and one closer to us. With such a directed light, that is the output that we get. But the base color is, well, incorrect as well. So let's go to place where we render things. In here, when we are copying this, we push constants, we say entity.material.texture. This material that we're using is the material from PBR, from the entity default. This shouldn't this shouldn't be there. So cut this and move this to models. So we go back into the model loader. In fact, mesh also is no longer used. Model loader is around here with the H file, primitive model mesh, material. So we put material over here. Texture ID, which does need an include. That should be fine. We have the material now. So instead of using materials from somewhere random, we will check. So if current model dot materials, not actually not like this. We're doing current primitives. Primitive dot material equals un32 max. If equals un32 max, then we use the default material. Okay, we're going to use default material often enough that it's actually worth creating a default as a static value. So material static const expression const so static const expression material default equals like the absolute default value, right? Lot of problems now. A new undefined type material, of course, because it doesn't exist at that point. Mesh is not a thing for entity to be constructed on. Entirely fine, so we'll delete entity altogether, that constructor of entity. Member function will go to this. So you can see material doesn't exist anymore. Build, rebuild solution. Okay, some syntax errors still. Expected this. Oh yeah, we didn't finish this. So if primitive materials is event max, then we use the default material. Else we take the material and we do primitive dot material. So that gives us the current location, the current material. So I'll put it like this. If it's not equal to event max, then we push these materials. Instead of entity.material.texture, this will take primitive.material. No, this will take this one. So what I'll do here is I'll just take material as a pointer, mat equals materials. So we index it, we do an ampersand on it. Well, material, that should be fine. Mat is never used. Localizing with the wrong type, also fine with us. Now we can do std byte no, offset of mat comma texture, or we can make a constant in there. So we can say sampler. So const expr static begin offset. So GPU data offset equals size of sampler. Static size t. Okay. So now what we can do is we can take the material, we can cast it to a byte pointer. I don't want to keep saying stud byte every time actually. So in math util, using stud byte, right? So I just say stud byte as a using. That way I get to just be here. So now with byte pointer, we can say material data equals mat reinterpret cast byte pointer. We need a const on this, so const again, because the data we're looking at is const, right? Now material data plus equals the offset. So what's the offset? Hold on a minute. Yeah, that's fine. Material data plus equals the offset. What is the offset? The offset is material GPU data offset. So now we move material data up, and so we can write this. So this one becomes just material data, and this PCB data size becomes material size. So size of material minus material GPU data offset. I don't not particularly enjoying that, so I'll say GPU data size, and this will be equivalent to the remaining. So I can't actually do size of material here. This doesn't work because material is not completely created yet. So there's no way I can have this as a const expression without just manually computing it. Or the way I will write it is size of texture ID plus size of UN32T plus size of float plus size of float again plus 2 times size of float plus size of XM float 4. This can be wrong, but we can put a static assert here to check. So static assert GPU size of material equals size of no, not size of, but GPU data material GPU data offset plus material GPU size data size. There we go. So now that's guaranteed. So with that, I can say GPU data size. So GPU data size, and I don't need this anymore. Build solution. So if it's not that, we need an else case. So else, thing we try to remove. So material is not a member of entity. Material goes away from here. However, when we do delete models, we now need to go through every material. So for auto and material inside entity model materials, for each material dot texture, we need to destroy it. The p render device texture manager pre texture, and we provide that in. This needs a move. That's it. Build or start. That's not right. So another thing that is probably occurring is I'm not sure if we are doing the process material properly here. So material index, when we are adding primitives, we want to add that. We're not doing it there. We should be doing it up here. So after index buffer, we should do it. We'll put it comments index buffer material. We get a material index, we process it, we get the new material index if there was a primitive dot material. Then for pushing back, we give this material index in here. Start. There we go. That is the right one. That is what we want. I'll swap the rotations now. So swap the rotations now. So inside mesh, not here. Where is it? Blaze.cpp. Sorry, inside blaze.cpp, I will take the top level matrix transform iteration thing. I think I do it up somewhere. So for each entity manager.iter, instead I will take root. Oh, there's no iter root here. I did do an iter children, I did not do an iter root, huh? Manager.iter. Okay, so I'll just do a thing which is entity dot is root if it's root. Then and only then do I need to do this. Alternatively, if not is root, return no continue. So now it will only rotate in one dimension. There we go. Ooh, finally, we have a cube that rotates. Hmm, mesh.slang. I have this little light factor here, but really speaking, it should always have some additional, which is known as an ambient. No, that's not gonna work. Build, rebuild. Now I run it. There's a little bit of a shadow of a thing you can see. We can increase this from 0.05 to zero point 0.3. It did point 0.3, right? Let's try 1. That is, oh no, this is entirely wrong. Like it shouldn't work. No, not shouldn't work, but it look very wrong. Not, yeah. Now you can see it actually darkening and going backwards and stuff like this. But ambient light shouldn't be zero point 0.5 normally. That's too much ambient light. Let's do a thing. Let's move ourselves 1 unit up on the y-axis. So in here, I do a camera data somewhere. There we go. So camera position, I can move ourselves 2 units up in the y-axis. Start there. So now we can see how it looks as it rotates. Okay, that is one model loaded. Simple type of model really. We have other models available in part of like the GLTF samples, as a part of the GLTF samples. So if we go through it, box, models box, we have the box textured, box with spaces, etc. etc. So textured, so we can now pull this out and see if we can get that to work. I already have box with textures pre-built, so let's try that. Model loader, no. Yeah, model loader.h, model.cpp. We go for the textures in there, and blaze.cpp at the top somewhere here. Yeah, box with. I think it exists. Assets model box with textures. Let's see. The folder view, assets, models, box texture. It's called box texture. Okay. So with that, we should be able to run box texture. Run. No, it's current document. Uh, we'll cancel the current thing. That's better. So we start this. Okay. It shows up white because we don't have the default texture, like default material, right? The correct material never actually loaded. So we have this. We never loaded the texture data. So what we can do now is we can say material.pbr metallic roughness dot texture base color texture dot texture, and here I can do for image. So inside image there's other things, but for now I can just say auto pointer img equals that. Start. Got to image, pass img. Buffer view gives us a nice little view. The URI is null. What's inside buffer view? So there is a buffer, there's an offset, there's a size, no stride. Buffer itself has other details, but without stride, we can't entirely get the buffer out. Plus, it says buffer view is invalid. So I don't think I'm supposed to be loading it from the buffer view at all. Huh? It's a PNG image coming from the buffer view. Oh, so the entire buffer view is the PNG image. Sorry if anybody found that to be like I'm shouting, but it was a little exciting. So STB image, we don't need it here anymore anyway. So we go back to model loader, just the .h file, stb image. Okay. Actually, we don't need it in the h file. We need it in the cpp. Modulo.cpp. Go up there. Add stb image. Should be a part of all of those. These, on the other hand, should be above all of those because those come from standard library. And these at the bottom because this is from me. Algorithm. Yeah, that makes a lot more sense to me. Now, S C T S T. What's wrong with this now? Does not match coding styles. Is that what you want? That is in fact what it wants. But CGLTF is a before D. Ugh, whatever. Caps lock is before, I suppose. This should be like this. Whatevs. Let it handle itself. So CGLTF implementation is stuck in this instead of the header only implementations. So I'm going to add it there, new item. Source CPP instead. This is this is CGLTF It also goes inside Blaze. Add. Okay, there we go. Stack define CGLTF implementation that include CGLTF.h. Alright, and with that, when we go back to mesh loader, we don't need this anymore. And it can sort itself as it wants. Okay, better. Now, let's look at what I want. So out here, I need to load this image. So I say stb I image vi load png. Okay, stbi load takes a file name because it's calling file. So we need this one. So it takes a buffer, which is img.bufferview.data if present data, otherwise buffer. So the way I'll do this is if img.bufferview.data, then do one thing. If it doesn't exist, else img bufferview buffer data plus img bufferview offset. That gives us the offset of the buffer location. So this becomes the size. stbiuc pointer data equals that. Void pointer. This actually needs to be reinterpret cast to byte. Yeah, stud byte, thanks. This also becomes byte. Actually, in math util, instead of using stud byte, I'll say using byte equals stud byte. Naming rule type tab. You can do byte t or I can do that. I can call it byte t. I don't mind having byte t. Right? That's it. Reinterpret cast. You start a cast instead. That's expected. Nope, let's do byte. Inconsistent naming, change naming rule, add all lower, save. Cool. So that allows me to do byte. We don't need the parentheses anymore. That's byte data, then the size. So size equals img buffer view buffer buffer view size. There we go. Okay. Now here, if it is an extension, buffer data exists, then data equals the buffer view data. Was with some static casting, and size equals this same thing actually. So in reality, I can move that out. I can also move byte pointer byte out here, and then I can. This is data. Data. It already exists, so that's done. We got size and data. Now stb load from memory. Now it takes a buffer, so that is data. Takes a length, which is size. Takes an x, y. These are inputs. So x, y, num, nc, 4. That gives us stbiuc pointer data equals that. Cool. This needs an stbi free, so stbi image free. Yeah, load. So that's data right there. What's wrong with this? Data already exists. Sure. So this will be image, image. Okay, now whole thing here actually can come from the thing we did before from Entity Manager CPP where we loaded everything. So we can start all the way up here. The staging buffer, let's create texture, create sampler, texture data. So right here. So we can start from this location until the end of all of this where we create the material. We far back, so miss data, no, model loader receive here. So here we load the material. We uncomment all of that because one must uncomment all of it. Okay. Ask for a texture file. Instead, we'll replace all of that with load from memory. So this goes there. Memory becomes data and size. There's something called data already. No. Reinterpret cast it. There's no problem in doing that. It's all bytes. This is also unsigned tar, which is just byte with extra steps. If not texture data, yeah. So if this happens, if there's any issues with loading it, we return you in 32D max. That says that this particular texture doesn't load. Okay. What else? Render device dot device. So it's trying to create a sampler using render device. We haven't passed render device down here. We will need it. So alongside model, we will pass render device pointer render device. Okay. Render device does that. Go, go. Mesh.buffer is trying to free it because, again, this is a failure thing. Return u in 30 to 60 max. Image load from memory here is no longer useful because we do it all in there. STD for transfer things. What's the problem with this? Because we don't have included array. Go up there, there's array, should be there. Cool. Don't need iterator, so delete it. What else is there? Frame in use. Frame is incomplete. Include. Okay, last. STBI image free. Don't need that no more. Because STB loads it inside. The texture data is already done, so we don't actually need it anymore. Yeah, okay. And this is supposed to get a frame, like fetch one of those frames, load everything, and submit it. So when we finish here, the texture is completely loaded into the render device, right? So we just need the texture RID. It needs to come out of this location. So yeah, here, see texture ID, texture RID. I will just move it outside. So out here somewhere, this, all of this can go inside. Let's not pollute the external part. Texture ID, base, color, texture. And in fact, I'll leave this image outside actually. The CGLTF image. Okay. And I can do that as base color image. Okay, so we have base color texture there. The texture here becomes base color texture. Base color texture again. Fetch image is base color texture. Those MIPs will handle themselves. All right, this is fine. So at this point, we will have texture. So texture can just move here. STD move texture, base color texture. There we go. And sampler, again, we have the sampler, but we'll have to fetch it out. So sampler, there we go. Move this outside. We're good to go, right? So now who owns the sampler anyway? So the sampler is owned by the material, which means it has to be deleted with the material deletion, which is being currently done by entity manager. That's not good, but it is what it is at the moment. So we'll first finish it using this, and then we can refactor it. So within material, we free the texture. We also need to free the sampler now. So we don't need all of that. vk destroy sampler device takes the sampler, which is nothing but material.sampler. We have to take it and null pointer for the allocations. Cool. That should work out. Build solution. Okay. Something failed. Process material is unresolved from external. Yeah, because we didn't add it for the main thing. Model loader CPP. So these are not in line anymore. And you know what? That's costing me a lot of effort. So instead, what I'll do is I'll take process node, the entire definition, move it below, move it above here. It needs process mesh, which in turn needs process material. But first I'll take process mesh and I'll move it all the way up here. Then I need process material there and move it all the way up here. It's the descending order of a drill down really. It's more of a build it up on the calling stack. Okay, build solution. Now let's see what's happening. Process material does not take two arguments because it now needs the render device. So render device. We do have a render device up here, don't we? Oh, we never passed it in. Render device, pointer render device. And we pass that through. Render device goes in. This doesn't work anymore because this wants a render device. This too does not have render device. Blimey, that's a big deal. So node itself, process mesh has a render device. This process node needs a render device. So render device pointer render device. Okay. And finally process node itself doesn't get called because there's no render device. But that's fine because process process node there. The order of entity manager and render device is not important, but I think I want to keep it consistent overall. So you get the render device in there, right? So all of that is done. Now, with based on this, model loader.h needs a bit of change. So model loader.h, because entity manager and render device are on different directions, different sides. Okay, that's it. Build solution. C style cast requires conversion. Where does it require conversion? Yeah, because we called it in the wrong direction. Okay, build. Okay, done. Start. Still white. The texture is definitely loaded now. Or so I say. I say it's loaded, but it's not necessary. So let's check. Node, save texture. Let's see inside. Okay, it's captured already. And when we go in here, pipeline state, FP is not what we want. Color pass, we go in here, we see there's this variables, texture ID, and it does have an internal ID, right? 64-bit internal ID should work, generally speaking. Texture viewer, it does have that. So it is trying to sample this. Now the question is, are there indices? And the answer is no. Texture, the UV of the material has not been loaded at all. So let's get to that, right? So specification, actually not the specification, but the model. So we go into the model here and we look at the GLTF. In here, with the not accessors, not all of this, textures, buffers, what do we want exactly? Details as a base texture. No, the accessors here. So text coord 0. So there is an accessor now that has to be manipulated. That has to be loaded. So inside model loader, it's something we already have. We already have a feature for texture coord. We just need to add it. So we do position, we do normal. Just in the same vein, we copy it, we paste it. So that goes away. This becomes text coord underscore 0. It'll just check it if it exists or not. Now, text coord is a bit different. This is R32F, that is normal, but this will be vec2. Alright? Because it only has two components. It should only have two components. Instead of normal, we'll call this text coords Okay, I won't number them because we will just end up having the same ones over and over. Just text chord attribute, right? Vertex dot plus text chords dot size. This is fine for each vertex. It doesn't have XM3. It shouldn't have XM3. It's XM2 now. Node count should also be 2, right? So, like text chord resize should be by 2 instead of by 3. And that will give you the right number of elements we want. So based on this, again, this is saying normal. This will actually be text chord. This is float 2. Float 2. It's trying to attach it to normal when it has to attach to text chord 0. With that, it should load itself. We'll see if there are any errors. But so far, this is fine, right? It is going from point A to point B. It is trying to load itself. It is wrong. I will say that much. It is wrong. But that might also be because of one of these weird thing that we're doing here. See, text code times 2. Build, rebuild solution, and start. That's it. Textures have been loaded. We have texture data. So what next? What else is waiting for us? So let's see. Source, repos, Blaze, assets, models, ls, box textured, box vertex color, and then there is the more interesting ones. So first let's do box vertex color because box series of things is easy. So inside Blaze here, change this to box vertex color. So colors. We're not loading vertex colors right now. If I rebuild this and I run it, we don't have anything. Wait, what happened? We don't have anything. Why don't we have anything? So again, friendly neighborhood render doc. And we can see what's up with this. Color pass, it is trying to draw something. It is drawing something. This is fine. So what is it drawing at all in here, right? MIP is okay. We're not going to touch the MIP. Panels are RGBA, that is also fine. Tools. Oh, there is a dark one. I'm not going to use it right now, but things to know. Okay, it is drawing itself. The normals are okay, they exist. Text code is 00 everywhere. That is fine, just fine. If I go and check the variables here, texture and it's 0, so that would take the wrong, not wrong, but like the other side. Base color is 0. This would not work. Is the base color explicitly 0 in this? This is textured. Box, taxi spaces, textured vertex color. And we can check in here. The ordering of everything is weird, but shouldn't matter. Color 0 takes 3, that's fine. Does it have materials? So primitive does not have materials. Okay. Default materials has 1, 1, 1. So it shouldn't be taking 0, 0, 0 at all. The only reason that can occur is because the default material we wrote in the materials is not actually correct, which is possible because I just said go default here. So you see like this material here in the default, it's not, no, this is set. This is set. Okay, let's check here. So default. Oh, we never passed it in. So if model is null, nothing. This push constant, if material is null, so primitive material is null, there. We need to pass the other alternative, which is the default. So here material data, this is material data here. So what I will do is I'll say byte const pointer material data. Okay. And so push constant will come out. It will do material data irrespective of what might be there. It won't be because if else. So here we take material and do the thing. On this one, material data is nothing but default material. So material default. Hold on. This material was not constructed yet. So material is default material, takes the address of that, needs to do a cast. So dot recast. Yeah, cool. With that material data set up, now we offset material data a little bit. Okay. And with that, we should be able to send material data in here. What's wrong with this? Assigned value is never used. Why is it never used? Ah, okay. Cool. Now material data is set up. This is good for now. If we start, it should work with 111. So it should give us a white cube. There we go. Its axis is a bit off. Unsure if that is expected or unexpected. We can check that by going back to an older box, one that worked. This gives us an exception because we tried to go to texture.image. I think, yeah, texture was null pointer. So first if texture, right? So if material PBR metallic roughness base color texture dot texture. So if texture even exists, only then do we want to go inside this whole thing and process it. Cool. Build solution. One failed again. Potentially unanalyzed sampler used. Null pointer. That's fine. Build solution. Okay, run it. Let's see where it rotates from. It does rotate from the center. So in this case, I think it's just a matter of where it stands, like where it is oriented. And box vertex colors just seems to be oriented away from center. This is all right. Now we need to load vertex colors. And as you know, our vertexes actually do not support vertex colors right now. Vertices. So inside model loader.h, we go to vertex. We have this directx xm float 4 vertex color 0. Now there's a little thing. So I say this is a color 0, that's a texture 0, and so on. But for models that don't have colors, they will waste this space. For models that don't have textures, they'll waste this space. So this can be simplified by having different vertices, different vertex types, right? Each with their own descriptions. And then when we create the given pipeline, we pass what kind of a vertex we will use. So we'll do that later, but right now we'll just use this. Because another issue that the mixed pipeline thing does, another issue it gives you is that shaders also need to be customized for that. All right, moving on. So position, normal, text coord, and color. Fine. Nothing else here needs to change. Inside load model, we need to change things. So if we go inside load model, so this is process materials, that is fine. Process mesh, there's text coord. It's literally again the same stuff. Instead, it checks color 0. Okay, attributes color 0. Again, color needs to be, if I remember, if I see it correctly, GLTF spec, color 0 must be clamped between 0 and 1, all components. When it uses that, the color n can be vector 3 or vector 4. So I will take an assumption of vector 3 right now. Okay, and this goes back here, back to 3. Float count is fine. Then float 3. This becomes color attribute. This XM float 3. Color. Colors. Okay, colors will be written there. Colors.size, all of that is fine. This will be color 0. This will be colored. And this will be color. Okay, color 0 here is an XM float 4. This is XM float 3. So let's not assert this. Okay. Here instead I will say if assert it equals this thing or color attribute dot data type equals cgltf vector 4. It has to be either one of these, like one of these two, but we will assert it just to be sure. Now, if color attribute dot data type equals cgltf vec3. So this is the vec3 version. We already have it, so we'll just write it more or less as it is. Here, instead of saying color like this, we'll say color dot x, color dot y, color dot z, and 1.0 as it should be assumed. And else, it's else because there are only two options. And here we will copy all of this, paste it. XM float becomes 4. Float count gets divided by 3, by 4, and float here becomes by 4. And these colors start getting directly assigned. So build, rebuild solution, right? Succeeded. Start. Okay. It won't use anything because none of this data is actually sent to the system. So in miscellaneous data CPP, inside these bindings that we have up here, we'll have to add one more. So text coord is done. This will be color. So color 0. Instead of RG, this will have B and A 32 floats. Location will be 3. Vertex input rate will be vertex. Stride is vertex, that is automatic. So now it takes that. And inside mesh here, I can take float 4 vertex 0. So color vertex color 0. This is vertex color. Okay, vertex color is there. Output dot vertex color 0 equals vertex color 0. There's nothing to be done here. And on this side, on the other hand, things change a bit. So I need to read the spec. Color n, color n, vertex color, vertex planned implementation should support to this thing. Okay, one vertex color, but how do we use vertex color, right? We can check base color factor. This is a definition to how base color factor is used. Texture is not given. Assume to have value 1. If factors and textures are present, factor acts as a linear multiplier for texture. Okay. X color. If vertex color using attribute semantic color 0, then value acts as an additional linear multiplier to base color. Right? So then here when we do any kind of coloring, so this actually needs a bcb.base color multiplication as well. And on top of this, we will use the interpolated colors. So there, float 4 interpolated colors. Vertex color. Yeah. And here I'd say interpolated color. There we go. So we have to multiply that by color, here base color and vertex color again. Build, rebuild solution, just in case, and I run it. Start. Those are vertex colors. This model is being lit up. It's actually an unlit model. So I'll remove this light factor stuff here. Since we don't use it, we can remove that too. And that. It's fine. Build, rebuild solution. Start. And there it is. Okay, so it's a good reason why they have set it at 0, comma 0 as the origin is because the vertex colors are the same as the vertex positions. So black is 0, white is 1, comma 1, comma 1. Then you have, XYZ becomes RGB and you get the colors and locations. So when we rotate it, it like rotates a bit weirdly. But okay, so that is how much of the spec we currently support. X code 1, so text code 0 is supported. We need to support text code 1 according to the spec requirements, but we can do that later. Let's move to orientation test. So this will test if our node orientations are working properly or not. Orientation test. There's a probability this is wrong. Like it doesn't work properly, but we'll see. That didn't work because non-uniform scaling is not supported. It has a scale, but it has a non-uniform scale. We can't just use it directly in our system, our current system, right? So let's go to the transform and change it. Let's change it to support proper non-uniform scales. So entity manager, no, it's a part of model now. So it's still a part of entity. So entity manager.h transform is up here. So it currently takes a float 4 scale, which is empty right now, a float 3 scale and vector, which is tightly packed. But I'll change that into directx xm float 4 on scale. This will have to be 4 as well. I have 2 points of data available which are not used at the moment. Can't really help it, right? So we will just use this for now. We'll just get along with this for now. XM, if you're using this, might as well use XM vectors. Okay, let's go back, build, and solve all the problems. There's gonna be quite a bit. Okay, first, local transform.position is being separated, which we don't have, right? Because it takes a translation, needs an offset XYZ. But I can just do XM matrix translation. Translation from vector, right? And there I can give it local transform dot position. It should be translation. Translation is more accurate because it's a transform. It's not it's not position. It's position in a particular space. Scaling vector. It takes a vector now. Local transform dot scale. So we can remove that. Okay, that simplifies things. There's also a full like transform option, like directx xm matrix transformation. So you can give it scaling from origin, scaling orientation quaternion, scaling. So you can give it an origin, then how we orient the scaling from that origin, then the scaling itself, etc., right? XM matrix local a fine transformation. Yeah, this is what we actually do. So here I can just say local transform dot scale, local transform dot rotation, local transform. Oh, it takes a rotation origin. We'll do that later in a sec. Rotation transform dot translation. All of this multiplied by parent. Okay. Now this needs a location position, so we'll give it vector origin, xm vector. There we go. Rotation origin is xm vector 0. Size t. Yeah, that's okay. Translation, create entity. We've given it xm float 3. Should be an xm vector. Since we already have xm vectors now, I'll move it out here. So everything can just be xm vectors. Right? And we don't need to do this assignments anymore. Similarly here, depending on what we get, so translation is xm float 3 here, but depending on this, we can say x directx dot xm vector set translation 0. Copy that, copy. Finally, translation is 1.0 on the last one. Okay, so that gives us the translation. Here I can just say xm vector 0. Okay, This is V translation, so I'll change it to V translation. Q rotation remains the same in either cases. As scale is a bit different because now we have a new scale altogether. So V scale equals node dot has scale question mark directx xm vector set node dot scale 0 and these will be 1 2 and 1.0 on the last axis, or directx xm vector 1 vector splat 1. 0 1 2 and 3 are all equal to 1, so that is basically it. This is correct. Fine, so that's what we want. V scale, all of this is done. V scale and everything is set there. So translation becomes V translation, rotation becomes Q rotation, scale becomes V scale, and I will change this a bit because transform dot translation with KC, what's that there, designated initialization, okay, V translation, Q rotation, scale is V scale. Cool, so that's done. What next? Build, rebuild solution. Now this translation and stuff, it's not going to break anything for us because rotation appears in the wrong order. Yeah, okay. Was directx xm1 vector splat 1 there, and this will be xm0. So directx xm vector 0. There we go. Okay, build, rebuild solution again. Scaling, non-uniform scaling is now kind of supported, but something went wrong here. What went wrong? Incoming transform has a translation, which is 0 rotation, which is the quaternion there. So what went wrong? What are you trying to read that doesn't exist? Create entity with a transform, takes a transform from outside. That comes from here, gives it a V translation, which is set in one of these two, right? So no matter what, V translation guaranteedly exists. If has matrix is 0, so we go here. Has translation also was 0. Okay, that would have set this to vector 0, which it did. Q rotation, quaternion identity should have been set on this. It is set. V scale should be set to splat 1, which it is. So translation, rotation, and this thing are set to the right ones. Zeros, 1s, 1s. So when we tried to create entity, something seemed to break. Okay, I have a little hint. Let's see. Run this. No, it didn't work. Fine. So is this, yeah, this is a valid value. Transform has a valid set of values here. So why ever did it read 0xff at all, right? Those both exist. Like, what's happening with this thing? Okay, let's try something. Take transform by value. Create entity. Take transform by value instead of anything else. Build solution. Okay, start. Okay. No, wait, this the constructor for the entity, not create entity. Is this that is giving me some issues, eh? Start. Okay. Create entity. So we pass that through this entity. This entity is unable to read memory. What's count? Count is a weird unknown value. Okay. How did we get how did we get here? So we try to know load that inside app in it with entity manager. The entity manager is here. App state is completed, so entity manager should exist. Load model, fine. Entity.addChild is trying to do that. What's the entity here? So entity is the one we created in this one. And this worked, right? So this actually creates an entity. Entity manager, entities in the count has completely gone haywire. So let's go here again. Start. All right. So now entity manager count is 0. We go in. Yeah. Go in, go out, go in, go out, go in. Okay. That comes to create entity. So we take entities here with we have a count here. So count is 0. Count is 1. Entities is something. We write entity transform into this. Count is still a valued value. Entity is a valid entity. We return. So an entity has been created by entity manager, which still has a valid count. Okay. Entity is fine. We're still fine. Now here we try to create a child for the entity. So entity process node, construct all of those. We try to create an entity here. That worked out actually. So entity manager count is 2. This is fine. Mesh, model mesh, child index. So it tried to add child, return the valid entity, did it? I think it did. And entity has, no, sorry, entity manager has count 2. Capacity is 10. That is probably where it's failing on the capacity. So what I'll instead do is I'll go to entity manager, and in entity manager, when you try to create an entity, entity manager CPP create entity, you just stop here. So now count is 2, this is fine. Count is 3, this is fine. Count is 4, this is fine. 5, 6, 7, 8, 9. Alright. So now the count will be 10. It creates this entity and it returns it to us. There is the bug. Assert count less than capacity. We can't create more than we have capacity for. Remove this, continue. There we go, right? We asked only for 10 entities in our creation by app state. The app state here, when it created it, just set capacity 10. So it had an error. This should be fine. So this is working. It's rendering something uh, allegedly. Save capture, run it. Something is captured. Mesh viewer. It's all over the place. Let's use a basic one. Ooh, how long has this been? 4 hours. What the hell? I entirely got stuck in this and I didn't pay attention to the time. Gee. Okay. I'll just finish it with one thing. So here I'll go back to box to test if our new orientation system is working or not. So it's not anymore, and that is not a good thing, right? It has to work. So, okay, we can check that. Close it. Mm-hmm. Color. There we go. Mesh viewer. So that's the mesh. That is the output mesh. So it is oriented properly. It's just not rendering for whatever unknown reason. Let's see the unknown reason. Load the images, pipeline state, push constants. Hey, that looks wrong. So transform, no, it doesn't look wrong. It's actually fine. But it is invalid. It is corrupted here. It is corrupted here. Let's see what else have we done in this. In box, we can leave it there. This transform construction that we did, that was a relatively big change all at once. So that's here with affine matrix transform. Rotation scale, rotation quaternion, that is fine. Rotation origin is xm0. Okay. And it is multiplied by parent. Let's try it with the old school thing. So xm xm translation from vector. This gives xm direct no, it says local transform dot translation multiplied by directx xm matrix rotation Union rotation matrix. No, that's the wrong way around. Matrix rotation quaternion, and that takes local transform dot rotation. Finally, directx xm matrix transform scaling, and it takes the local transform dot scale multiplied by parent. Okay, that's the scale. Takes three yeah, scaling vector. Okay, let's see if that worked with the old one. It doesn't, not anymore, at least. Something wrong with the transform, perhaps. So this has a 16-byte alignment. I can say align as, so align as 16. Okay, whatever. Static assert align of transform equals 16. This is fine. So entity static assert align of entity equals also 16. At least needs to be 16 really, but will be 16. Yeah, the line of entity is also 16, which means all entity indexes will be in the right places. I shouldn't have any issues with loading this into the transformations. The only other option is the construction in node processing. So model loader, where we process the node. So we process nodes. This node. We take a scale and we say non-uniform is not supported in the v-scale thing. That's no longer true. But we do it here. So we do check this here. So start. Okay. Translation gives me 000. That's fine. Scale gives me 111. So that's expected. We can just jump out of it. Jump in near Blaze CPP, wherever we were. So it's somewhere down here, right? Continue. So world transform is this weird value because it's not initialized yet. Now it should be initialized. And it is a fine value. It's not a fine, it is a fine value. So that seems accurate. But it doesn't matter until it comes to VK draw index, right? So we continue. Now we have hit draw index. So all we care is the world transform at this location. And there you can see there's a very small value over here as a part of the scaling. So something somewhere went wrong in the entire process. And I'm not sure what. So what I can do is I can check XM scaling. So XM scaling vector. X axis, Y axis, Z axis, it doesn't care about anything else. So all I need to have is X, Y, Z correctly, which we do. Translation. All of these seem to be in the right place. What's going wrong? Aha! Translation matrix from vector will construct a translation with the wrong homogeneous coordinates at the end. Because it's a zero, it's a proper zero, which is not what we want. So, loader, process node. In here, when we take a default translation, we don't want that. XM vector W. Let's plot W. Well, set it actually to 0. So let's go there. 0, 0, 0, and 1.0, right? Would be the default, so we'll set it to default. Run it. Let's see if that actually worked. Otherwise, my hypothesis was wrong. Hope it is right. World transform. No, it does have the negative 10 to the power minus 8 for whatever reason. So we'll fix that later. For now, we'll just take the scaling from, we can say DirectX, XM matrix scaling, and scale 1 is 1.0, 1.0, 1.0, and let it handle based on that. So we start. That's not drawing anything. In fact, it's giving us troubles. Did I say 0 instead of 1? No, I did not. So scaling of 1 seems to also still cause the problem. Hold on, there's an issue with streaming. Anyway, I'll stop here We will continue on next time. It's 4:20. I think that's a decent time to stop. Eh? So see you guys. This was nice having you around here. Ciao.